This research paper proposes the use of univariate polynomial regression as a function class to explore in-context learning, prompting, and alignment in transformer-based architectures. The study employs a GPT-2-style model with 6 layers, 4 heads, and an embedding dimension of 128, totaling about 1.2 million parameters. It introduces a simple yet rich enough toy problem that allows for clear visualization and understanding of these concepts. The authors train base models on random linear combinations of Chebyshev polynomials, which provide well-behaved polynomials with y-values within the interval 1, 1. They sample weights from a standard normal distribution and employ parameter-efficient fine-tuning by sampling weighted combinations of Chebyshev polynomials of degrees at most 5, fixing between 0 to 5 of the coefficients to be 1. This creates a task occupying a subspace of the original training distribution, providing clear room for improvement. The paper also discusses related works on prompting and alignment, referencing Xu et al. 2023, and Petrov et al. 2024. It highlights the power of toy problems for more crisply highlighting the limitations of fine-tuning methods. The methodology includes training models on a constructed task that follows the in-context learning structure as in Garg et al. 2023. The task is of the form x1, y1, x2, y2, x_query, where x values are scalars sampled from u1, 1, and y values are also scalars. The authors aim to showcase that a model could be aligned within this toy domain and make the case that studying alignment in this context is reasonable and can give a better understanding of alignment. The paper explores the learning of linear combinations of Chebyshev polynomials in a toy problem setting, aiming to understand and replicate phenomena observed in large language models, LLMs. The study focuses on alignment, prompting, and jailbreaking behaviors using a GPT-2-style model. In the first set of experiments, the model learns to predict linear combinations of Chebyshev polynomials with varying degrees of complexity. It outperforms baseline polynomial regression and ridge regularized polynomial regression in low data regimes, indicating better conditioning. For alignment, the task involves clamping y-values at a certain threshold, mimicking real-world objectives such as controlling toxicity and question answering. The model learns this behavior well and demonstrates that it can be jailbroken by providing unaligned responses when queried with malicious context. The paper also compares the performance of two fine-tuning methods LoRa and soft prompting on a simpler task distribution. LoRa performs better than soft prompting in general, and the performance of soft prompting varies with prompt dimension and benefits from a narrower task distribution. The alignment experiments show that the base model can be aligned in context with a large number of aligned examples. However, it can be jailbroken with enough jailbroken examples, matching findings in LLM domains. These results, along with others, suggest that the simple task of polynomial regression could be useful for understanding in-context learning in large language models. Overall, this paper demonstrates the potential of a simple, low-compute task to explore complex phenomena observed in LLMs, providing insights into alignment, prompting, and jailbreaking behaviors. In-context learning, a form of few-shot learning, utilizes input prompts to guide models, enabling them to learn from few examples and adapt to new tasks. Recent studies have explored jailbreaking and guard aligned language models, which can be trained with only a few in-context demonstrations, and soft prompting, which uses a single, fixed input prompt for all tasks. The latter has been shown to improve the performance of large language models on various tasks. Curricula, involving training models on a sequence of increasingly difficult tasks, have also been found to be effective in improving performance when well designed and task-specific. The paper provides a detailed analysis of the distribution of a random polynomial with coefficients drawn from a normal distribution, including calculations for the expected value, variance, and probability density function, PDF. The results are visualized in Figure 6, showing the standard deviation and PDF as a function of x. The authors investigate the properties of normal random linear combinations of Chebyshev polynomials, illustrating the standard deviation as a function of x in Figure 6a and the corresponding distribution of y in Figure 6b. This distribution is equivalent to the sampled joint x, y distribution in Figure 1. In the context of shared points in the 5 shared coefficients function class, the authors demonstrate that using a linear combination of Chebyshev polynomials of degree 5 results in 5 fixed points, independent of the choice of the last coefficient, as visualized in Figure 7. The paper also provides supplementary information on the model and training configurations used in the experiments, including details on the standard model, training context length, loss function, learning rate, and evaluation methods for toy problems with soft prompting and LoRa, as well as the training configurations for toy problems with alignment. The authors employed a clamping threshold of 0.5 for all alignment tasks, utilizing hinge loss with a weight of 100 for points above the threshold to disproportionately penalize misclassifications. They also utilized curriculum learning, gradually increasing the number of input points to the model to learn easier tasks first, as introduced by Wu et al., 2021. This approach was also used by Garg et al. In their work on simple function classes as a toy model for in-context learning. The training process was performed on various computers, including a GeForce RTX 3090, and utilized the Savio computational cluster resource provided by the Berkeley Research Computing Program. The authors also used GNU Parallel, Tongay, 2018, for parts of this work. The baselines for the experiments were established using linear regression in Chebyshev basis, both without and with ridge regularization. The ridge parameter was set to 0.2, and the optimal estimator under Gaussian noise was used. The authors note that linear regression can theoretically predict the exact polynomial with n+1 examples for a degree n polynomial, which is why the graphs in figures 2 and 3 are cut off. The authors investigate the effect of positional encoding on performance and find that it has an insignificant impact. They also examine the effect of learning rate on performance for many soft prompts and observe that changing the learning rate has a significant impact, but does not solve the problem of poor performance. The authors chose a learning rate of 5e2 based on Figure 9. Additional graphs with linear scales are provided in Figures 10 and 11. This study examines the efficacy of soft prompt learning in various settings, including polynomial regression and fine-tuning on noisy data. Figure 9 presents a comparison of the effect of different learning rates on soft prompts for predicting y-values on normal random linear combinations of Chebyshev polynomials of degree 5. The results show that the learning rate has a significant impact on the performance of soft prompts, with higher learning rates leading to improved performance. Figure 10 evaluates the performance of a pre-trained model on normal random linear combinations of Chebyshev polynomials of a random degree between 0 and 11. The results demonstrate that the pre-trained model achieves excellent performance, even when the degree of the polynomial is high. The relationship between soft prompts and hard prompts is also investigated, with results indicating that the closest hard prompt in the embedding space does not preserve task efficacy. Furthermore, the magnitude of the soft prompt is significantly larger than the magnitude of the closest hard prompt. The soft prompt is found to be more sensitive to rotation than scaling, consistent with previous findings. Figure 11 compares the performance of fine-tuning methods on normal random linear combinations of Chebyshev polynomials of degree 5, with varying numbers of fixed coefficients. The results show that LoRa, learning to rank, outperforms soft prompting, especially when the number of fixed coefficients is low. Soft prompting is found to struggle with fine-tuning on noisy polynomials, which is attributed to its inability to capture nuanced distributional differences. The study also investigates the impact of model size on performance, with results indicating that larger models are better able to perform well on the clamping task. However, the optimal model size is not determined, and further research is needed to fully understand the relationship between model size and performance. The researchers investigate the efficacy of in-context learning for polynomial regression tasks, exploring the effects of soft prompting, model size, and context length on alignment behavior. Soft prompts are found to be sensitive to perturbations in scale and rotation, with increased sensitivity to magnitude and direction changes. The performance of LoRa and soft prompting on Chebyshev polynomials up to degree 5 is evaluated, revealing that as the number of fixed coefficients increases, the model becomes more expressive and better learns features from the shifted context. The authors justify studying polynomial clamping as a proxy for alignment by comparing its performance with other language model tasks, such as planning, summarization, and translation. The trends across these tasks are similarly monotonically increasing, supporting the use of polynomial clamping as a proxy. The effect of model size on in-context alignment is examined, showing that medium and large transformers outperform the small transformer, suggesting a threshold beyond which the model becomes expressive enough to learn alignment behavior from the context. A novel approach to aligning polynomials in the context of transformer models is presented, focusing on the task of clamping values in context. The study utilizes a transformer model fine-tuned for this task, demonstrating its ability to predictably outperform baseline models. The effectiveness of the proposed method is illustrated across various degrees, where adding a clamped context leads to good predictions. The transformer model is found to significantly outperform traditional methods, especially at higher degrees, leveraging its strength in understanding long-range dependencies and contextual relationships. The use of a transformer model in this context is novel and significant, and the findings suggest that this method could be applied to various domains requiring precise control over data manipulation and prediction. The importance of clamping values in context is discussed, highlighting its potential to improve accuracy and reliability of predictions.